How's it going? Getting PA5 sorted out? Awesome. All right, so questions on dynamic programming, PA5, anything? All right.
Would we be able to talk about the global variables and checking for how many times they're used in the recursion thing? Or how that may be more possible? Or
So you have a global variable, which is where you're saving your results, right? So the dynamic programming piece. And that's typically, so are you using a structure to save inventory and stuff? So we could have a struct answer, save bracket. So what's the maximum weight? 1024?
1024, yes.
Okay. So you could declare an array of struct answers. I would make it 1025 so you can index it with 1024 down to 0. And do some sort of initialization. Basically, this is where we're going to save each of our results, each of our answers, right? So when we go into our maxval function, first thing you're going to do is check to see if the answer for that capacity is already stored in here. So you got to have some way of flagging that. And one way to do that typically is to just initialize these things to say -1 or something, because we know negatives are never going to be a valid best value, right? The lowest case is going to be 0. So before you do anything, call a function that goes through loops in this and basically saves a value of, say, -1. And then in your maxval of capacity, check that element. So save bracket capacity dot whatever you call the field that has the value. Dot value is bigger than or equal to 0, then just return that value or that element from the save array. Otherwise, do your loop, do your recursive calls, do your comparisons, and so on and so forth. At the end, before you return that value, save it in that array at index capacity. And then next time you try to do the same problem, it'll just pull it from memory. Does that make sense? And you can make arrays of structures just like arrays of integers or characters. So you can say structure name, array name, bracket, how big you want it to be, and it'll allocate space for it. You can't make it ridiculously large, but 1025, no problem. If you want something with millions of elements, then you have to sort of dynamically allocate. And that changes how we do this, but for a few thousand, it's not a problem. All right, other questions? So Monday, presentations, right? This is pretty informal. The idea is just to basically, each group comes up, I'll bring in a laptop so you can log into the server. Come up and introduce all the people in your group. Show us your code running, so you can pick your own knapsack.data file, but make sure it's not totally uninteresting, like have more than one object in there or something. And just show us that your code runs with some example runs. You can talk us through your code briefly, but if there's anything in your code that stands out, if there's some aspect that you found particularly tricky or something that you came up with a solution to that you thought was you know, kind of interesting or imaginative, right, you can talk about that in detail. So it's really just kind of presenting your PA5 to the class. The other thing I want you to talk about, though, is the group aspect. So I want you to describe how you tried to break this project up among the different people in your group, how well that worked, if you changed the plan partway through, or if it worked great, or you know, everybody did their part, but then you had trouble putting the pieces together. Just kind of tell us about the whole experience. And additionally, I want one person from the group to upload to Canvas by the due date, right, so that I can go in and look at the code myself and run it. So is that clear? All right, well, let's keep talking about coding. So we started talking about Huffman coding yesterday. Is that right?
We talked about talking about it.
Talked about talking about it, okay. So now we're going to talk about it. So we were looking at compression, I think, when we ran out of time. You can take files, you can try to compress them in the hope of taking less memory than you might have if you just stored an ASCII code for each character, for example, or the 32 bits corresponding to each instruction in a machine language program. So compression schemes, there's lots of different versions of this. So a pretty common scheme is something called run length encoding. And if you have a file where some pattern or some character is repeated multiple times, you may be able to save space if instead of storing that character a gazillion times, you store it once and you say this is also stored a gazillion times. And this works really well with pictures, because if you kind of look at a typical scene and you kind of scan from side to side, slowly going down, you see a lot of repetitions of the same pixel side by side, right? Either because there's a whiteboard where everything's the same color, or we've got this silver band right here, which might be a repetition of the same pixel value as you move across. And these things will compress nicely using run length encoding. And we're talking about lossless compression. There's things you can do if you don't mind losing information. And like JPEG is a lossy compression scheme. You don't end up with an image that you can reverse back to get to the original image. Stuff is thrown away, but the stuff that's thrown away in JPEG is presumably the stuff that doesn't matter to your brain, because our brains fill in a lot of things when we process images. So it takes advantage of that. MP3s are lossy. They compress audio files, but in a way that supposedly isn't noticeable to your brain. Of course it is. But if you have cheap headphones, it's not as noticeable. But we're talking about lossless compression, where the exact information that's stored in the file to begin with is still retrievable from the compressed file. Okay, and that's a more particular subset. So run length encoding is one way to do that. So Huffman encoding is based on frequency analysis of pieces of your file. So if you're storing something like written text, right, we know that letters don't always occur at the same frequency. The letter E occurs much more often than the letter Z. Okay, and you can find tables of frequency of letters based on language. So in English, E is the most common letter. But we typically use 8 bits to store the letter E. We use 8 bits to store the letter Z. We use 8 bits to store a backquote. How many backquotes do you see in written text, right? How many tildes do you see in written text? How many E's do you see? So the idea of Huffman coding is if we were to use a shorter code for these more frequent characters and a longer code for the less frequent ones, you might end up needing less space. So Huffman coding, there's a particular way that we can take a frequency analysis of our text and use that to come up with a more optimal way to encode the characters.
It's kind of like CISC.
Like what?
Kind of like CISC.
I don't know, sis.
Complex instruction set?
Oh, yeah, yeah. Yes, we could do that. Yeah, that would be similar. So typically what we do first is we analyze the thing that you're asked to compress, and we do a frequency analysis. And let me give you a fictitious result of that. So suppose we analyze some written material, and we come up with the following frequencies. And this only has 7 letters in it because we've only got 15 minutes. All right, so 5321, 632, these are the relative frequencies. Higher number is more frequent. So E is the most frequently occurring letter. It occurs about 6 times as often as the letter D. Okay, these are just relative, so higher is more frequent. And we've got 7 things here, so we know with 3 bits we could encode each of these. But since E occurs way more frequently than D, if D took a few more bits and E took a few less, on average we would end up with a smaller file. Okay, so here's an algorithm we can use to take this information and come up with a coding. And I'm going to go through this, and I'm going to have you go on the board with another frequency table and work this out for yourselves in groups. So here's what we do. We always look for the 2 lowest frequencies. Okay, so initially these are the only things whose frequencies we know, these original letters. And the 2 lowest ones, well, definitely the letter D. And the next lowest could be either C or G, and it doesn't matter which one we pick. So I'm a computer, I'm just going to start from the top and find the second lowest frequency. That's going to be a D, C. Okay, so I'm going to write these down. I'm going to make them children of a node. So this occurred with frequency 1, this occurred with frequency 2. And the root node, I'm going to make that frequency the sum of the 2 frequencies. So I'm going to say this occurs with frequency 2. Okay, so now I'm going to compare frequencies 5, 3, 6, 3, 2, and 3. I'm going to skip the 2 and a 1 because I've already put those into my structure. But I'm going to include this 3 as a frequency I'm comparing to all these others. I'm going to look for the 2 lowest frequencies. Well, there's a 3, there's a 3, there's a 2, there's a 3. Okay, so 2 is definitely the lowest frequency. That's a G. The next one is a 3. I could use either B, or I could use F, or I could use this. Let's just go ahead and pick up the first one. So 3 and G. So I'm going to put down G with a frequency of 2 and B with a frequency of 3. So I'm going to mark those off. And I can combine those and say combined they have a frequency of 5. Okay, so now my set of frequencies, I've got a 5, a 6, a 3, a 3, and a 5. So what are my 2 lowest frequencies? So I got a 5, a 6, a 3, a 3, and a 5. So 2 3s, right? Okay, so one of those 3s is an F, the other 3 is right here. So I'm going to take my F with a frequency of 3. I'm going to take this with a frequency of 3. I'm going to combine those and get a parent with a frequency of 6. And I'm going to mark off F. You get what I'm doing? So we just keep doing this. Find the 2 lowest frequencies. Well, I have a 5, a 6, a 6, and a 5. Sounds like the 2 5s are lowest. So there's an A and a 5. And I'm going to put this over here just so it's easier to draw. So there's an A and a 5, and those combine to a frequency of 10. And the A is gone. So now I have a 6, and a 10. And the 2 6s are the lowest, so let me put the E with a 6 together with this 6, and that gives me a 12. And now I have a 12 and a 10, and those are the only things I haven't made children of anything, so those combine to a 22. And now the only frequency I have left is 22. There's nothing to pair that with. I'm done. And I have a tree whose root is whatever, but all of my original letters are sitting as leaves in this tree. Okay, so here's how we find a coding. We think of this tree basically, if you move to the left, it's going to be a 0. If you move to the right, it's going to be a 1. So beginning at the root, I'm going to move down to a leaf, and I'm going to record which way I travel to get there. If I travel to the left, I'll write down a 0. If I travel to the right, I'll write down a 1. So let's look at the letter A. I travel to the right, there's my A. So this is going to have the code 1, 1. The letter B, I travel to the right, the left, and the right, that's 1, 0, 1. The letter C, I travel left, left, right, right, so that's 0, 0, 1, 1. The letter D, left, left, right, left, so 0, 0, 1, 0. E is 0, 1. F is 0, 0, 0. And G is 1, 0, 0. And there's my Huffman coding. And the letters A and E are very short. They're just 2 bits, right? Which is good because A and E, those are my 2 most frequent letters. The letter D, which occurs very infrequently, a frequency of 1, that takes 4 bits to code. Right? Now, perfectly uniform coding, we could use 3 bits for each. So my very frequent letters take less than 3 bits, and my infrequent ones take more. But if I actually average this out in terms of how often each letter occurs and how many bits that letter takes, this is going to take less storage on average, as long as my text conforms to those frequencies. So there's a trick here. So first trick is this is a variable length code. So to parse a file containing a bunch of 1s and 0s, right, like this. I wrote that kind of small. How do we know what that represents? Because we don't know if our first letter is 1 bit, 2 bits, 3 bits, 4 bits, right? But this should be completely unambiguous. So we start with the digit 1, and it could be either an A or a B or a G. So we have to go on to the second digit, which is a 0. So a 1, 0 could be a B or a G. We go to the third bit, which is a 1, 1, 0, 1, that's got to be a B. No, it's not. But Morse code does something similar in spirit, which is it uses very short combinations of dots and dashes for frequent letters, like the letter E, and then longer ones for less frequent. So that's a variable length code. All right, here's a 0, so that could be any of these things that start with a 0. When we get to the 1, that's got to be the letter E. So that's an E. Yeah?
If K is just 1, 0, how do you recognize 1, 0, 1 is K or B?
Wait, say again?
If I add 1 letter is K, and K equal 1, 0, how do you recognize the K 1, 0, 1 is 10 is K or just B?
You can't. So that would make it ambiguous.
Yeah, that's my question.
Right? So this would not be a valid code, because now if I see a 1, 0, I don't know if it's a B or a G or a K. Right? So when you do this and you come up with your coding, that should never happen. Right? If there's 2 codes that begin with the same thing, there'll always be at least another digit after that that'll discriminate between them. And in this case, there's a code that has just 1, 1. No other code can start with a 1, 1. Right? There's 1, 0s, there's 0, 0s, and there's 0, 1s. 0, 1, there's no other code that starts with a 0, 1. A 3-bit code, FFF, there's no other code that begins with a 0, 0, 0. Right? So this is set up to stop it from being ambiguous. Now, if before I build this tree, I analyze my text and I find a letter K, right, then that will change this coding, and K will end up with some code that's unambiguous. This also means that to decode a bit string in this file, you need to know what the coding is. And so the coding is usually stored in the beginning of the compressed file. There's a dictionary that basically tells you how to translate the binary that follows. And it'll say this is an A, this is a B, or whatever. And you can do this based on frequency of letters, you can do it based on frequency of words, you can do it based on frequency of arbitrary bit patterns. If you were coding a binary file and increment instructions occur much more than left shift instructions, you might, find that that particular opcode occurs more often. Doesn't matter, right? So you analyze the file, you make your frequency table, you build a Huffman tree, you come up with the coding for each thing, you write the coding in the beginning of the file, and then you code your file using that coding, and that's your output file. All right, so you ready to try this? All right, so let me give you a frequency table and go up to a board, find some group to work with, and let's go ahead and use this set of frequencies. So we've got 8 letters, A through H.
No problem. And you also write the one. Next one. So you would be child. It would be parallel to it. The 2 children. It's like on the same level. Yeah, on the same level. It's going to be on the same level.
So CD is good, right? You put C and D together with a frequency of 2. That's right. So then you want to compare 2 and all your other frequencies and find the 2 lowest frequencies. So G has a frequency of 2. But this 2 is lower than H. It's just 3. So before you put the 2 and the 3 together, you should put the 2 and the 2 together.
So G would go next level below.
You get what I'm saying?
Oh, wait. I'm not sure. I think G would go.
It's very hard to go back and figure out how something came to be.
G would go up here on 2.
Because this was a 3, that 2 could go with either this 3 or that 3. I just chose to put it with that 3. So if 2 things have the same frequency, it doesn't matter which one you use.
Yeah, I'll second.
Yeah, and then, so for instance, right here, let's say we're right here. Take the next smallest number. So C and D we use also. What's the next smallest number? What's the next smallest number? 4. 3.
That's gonna be a 4 up there.
Yeah.
And then we've got a 3.
4 zeros and 1.
Okay, like
What's the next smallest number?
Right here?
Yeah.
Right here?
No, because those aren't on the same level. How does that work? They are on the same level. Oh, they are. Okay. So they're on the same level, and then the top one's a 7. Alright.
Since we already have 4, why are we putting the 4 here?
B actually.
Isn't this just become B? No. No. So you're gonna, I don't know what to do.
I guess it goes right here. And then.
So what is that number you do? No.
Which is kind of.
I mean, yeah, you can go about 4. I mean, let's just keep going, I guess.
Oh, I got it.
Look for again, no.
That could be great. Not really good tree.
Yeah, so what it actually did my instead of going up a level, what we should have done is maybe what we could do is and then we write this
Yeah.
Everyone else is okay.
It just so happened that the two
Yeah.
lowest, one was always on the sound of the tree.
Right, right.
Well, you can walk down the tree. They say you hit a leaf.
The next one was the 7.
Yeah.
1, 0.
So 1, 0.
So C and D gave you 2.
Wow, you have one for 6 bits.
Yeah, we just did another dots next to it.
C and D gave you 2. Okay, so 2 and G are your 2 lowest. Put those together and you get 4. So now you got a 4. You've got a 3 down here, so put the 4 and the 3 together. So make H and this children of another. Oh, you're right, my bad. Oh, no, B is still bigger, so you could either put, so H is the smallest, right, that's a 3. You can put that either with B or you can put it with S. Depends how you write your code, which one it's going to find first. Either one is perfectly valid.
You can choose to do that, that's fine. But
So you want to put it with B?
Put it in balance over here. That's the point.
So that's a frequency of 3, 4.
It's better like that. I'll give it a try. Because your non-sprinkle letters have the leaf are only 2.
So you put H and 4 together?
So when you balance it,
So
each balance
bring it
you
down.
get
Put this over here.
So H
More average.
so you see that there?
So that's 7. Alright, so you got a 7, 7, 8, 4, 10. So 4 is the lowest. And you can put it either with this or with F. So you put it with the F, you can just put it here and make them, or if you put it with that 7, you put it here and maybe this is make the children of a node, or you can put it with F and just have. Yeah, for a while.
Yeah, I was thinking about
See that what you got?
But I think it's a solution, but I have no idea.
What do you mean? The whole point is, it's down, doesn't do anything.
Basically, what's up above this?
That's all we were looking at it compressed.
Okay.
It might be compressed. If you had all the data for a character, it wouldn't be compressed.
Perfectly balanced. It would still be the
No, I'm saying that if you were to put in every possible value, then it would be zero. Right? If you balance it with every possible value,
branches, right?
Yeah, okay, so write down the coding.
You want to keep it wide.
I think that's a good treatment. How's it coming?
So we got this. Almost sure that can't
Technically, like, not in the right, we not on it.
Well, if you get C and D linked together.
Where do we have
C and D linked together. And then two the smallest one here is G, so 2 and G. Give you 4. So that's 4. You've got 3. Put that together with 8.
Yes.
7. Alright, so now our smallest one's
You balance it,
7.
average out the length.
You've got
So you can't lose
4.
the whole.
Yeah, most common, most common fills it off, so you're
7.
not losing it.
No, but if you look, you're only putting letters in the
Now
leaves.
you've got
Wait, what?
11. You've got 7.
So if you were to squash it, something that's balanced.
So you shouldn't be putting 7 and 11 together either. Because you've got lower frequencies that you could pick from, in particular 7 and 8.
Okay, so then you would go on this
So
side.
yeah, at this point, I would pair 7 and 8 together.
Okay.
That'll give you 15, and then probably the 11 will go with the 10. So you're good up to here, the rest of that is good.
So it's trying to keep the differences small between the
It's just trying to take the two lowest frequencies and pair them together basically at each step.
Okay,
The
okay.
lowest frequency of either your original leaves or what you got.
Why not just this try search tree with one for each? So you can start duplicating.
My code that I don't
Which one did that? Then you need the try search tree.
Alright, so did you come up with the coding for each letter? Based on 0 to 1? Okay, cool.
So it doesn't have like these.
You read the code.
It's useful, but it doesn't have this way.
No, that usually won't.
See, like the way
It would make you less have to get to.
Yeah, that looks good. Really good. Plug forward. Makes sense? Okay.
1 0 1.
Are those
0 0 1 2.
Yeah, so most frequent today.
That would be good.
Probably 0 0 1 0. Oh, I see.
Okay, so for fun, try with 8 letters, all with frequency.
So how do you know A is 0, 1, 1? Like,
0 1. Where the extras That's how I write my
Not very much. I've never seen that.
Do we not put H in there?
Log base 4, yeah, I think so.
It's strange.
Yeah.
I don't think anyone's gonna get the same result.
Yeah, Google it. Seriously.
No.
Yeah.
I'm changing my.
There you go.
Starting with A.
I mean, it's the same thing you did, right there.
Alright, so you got your code.
You wrote it
That makes
myself so I
sense?
can understand it, you know?
Yeah. Basically, like, I want to try to find the smallest, lowest frequency.
Basically, you're
Let's do them all.
You could do dead two.
Basically updating your frequency. Yeah, let's.
Okay, now that's more.
Yeah.
No, I have no idea what you're talking about.
Yeah. Cool. Alright, makes sense. Alright, so for kicks, try coding 8 letters all with frequency of 1. See what tree you end up with.
Okay, let's try that. 8 letters.
Yeah.
Oh, you Wait, let me tell you something. But letters and numbers, so you want 8 letters, okay, 30 seconds.
Well,
A1, B1.
so if you start with the 1.
I would believe we could do
Start
B
with
and B,
0,
1,
1.
2.
Otherwise it's a 0, 0.
That's a, no, we could.
Yeah.
No?
Oh, I don't know actually. I mean, you have to go back
No.
to just look if there's anything obvious.
It's shorter. There's only 1, 2, 3 rows.
Tell me your watch so this is like 0, 0, 1.
Yeah, I can show you.
Right away, that's not going to be right. Because you just start with 0, 0, 1. You wouldn't be able to tell the difference. But yeah, it's module.
That's saying that all your frequencies are one.
But that's what she just said.
Alright, so try.
That'd be-
Yeah, they can make all the frequencies 1.
The A would be 3 zeros.
Yes, we do it.
D would be
It's just gonna be the binary. Yeah. It's gonna be the normal binary.
Something like that. I don't know what the theory is behind the picture, but it's something that's like.
Yeah, that's the Christmas tree we got set up.
It fits in the shorter limits.
Maybe the munchkin or whatever.
Yeah, make them all one. You good?
We also did the wheel
Did the equal one, and you got binary, cool.
That's illegal. You can't do that.
Awesome.
Because you still have ones available.
What's the next option?
Oh, I don't know.
Can I ask where do you get your shirts from? The button-up ones.
This one I got from Amazon.
Oh, okay.
Yeah. Usually Kohl's.
I'm trying to like find more Pendletons
Okay.
or type of these shirts because it goes with my style. They usually go
Okay.
with. I'm like, that's a cool design.
It's hard not to just like go crazy on Amazon. And once you figure out the sizing, which countries have different sizing scales and stuff, then you can pretty reliably.
I usually go to like the Portland Liquidators
Yeah.
store down in Portland.
Oh, cool.
One of the Chinese like outlet stores.
Mhm.
And they usually have a lot of good type of prints. Anywhere from like a semi pseudo silk
Yeah.
that shines a lot
Mhm.
to simple stuff like this.
Cool.
So yeah, I was trying to find more. 'Cause
Okay.
I like the style of them.
Cool. That looks great.
I have absolutely no idea how I program that.
But you can do it on the board, right?
Yeah.
I'm pretty sure every one of them has a different answer.
Yeah.
There's a variety of answers. There's also a variety of how many bits you need for each one. So back there they got really long codes for C and D, and they got 3 codes with only 3 bits.
So,
And then some people got only 2
when you're
codes
doing this type of
with
coding,
2
you want
bits,
them to
but
try to
then no
be
6-bit
similar, but
codes.
have a very low difference.
And that's all valid.
With these type of codes and all this stuff, you want the difference between the two being very small.
Not necessarily. But effectively, I mean, since we're always pairing things with lowest frequency, but no, I mean, the difference could be huge.
Well, I know, I'm just
You might have
saying.
something with a frequency of 1, and something with a frequency of 100, and something with a frequency of 101. You're still going to pair these together.
Yeah, because
The difference is big.
because if you pair those together, you get 101,
Yeah.
and then you get the pairing of those together, which
Right.
is, you know.
Yeah.
But I was saying, like, you try to work towards having similar numbers between the two when pairing them to get up.
That's not that is really a goal.
Okay.
It might be an effect in general.
Well, I was looking comparing to like the original one where we did like this.
Yeah.
And then you said it was easier to have like the 7 and 8 paired off to the side, which was 15, which was 15 is closer to 21 than 11 is 21.
Right.
And that kind of stuff.
Yeah.
That's why I was asking that. 'Cause, like,
Yeah, so maybe that would give you a more balanced looking tree or something?
Yeah, it would give you more balanced looking tree and also kind of how we came
Yeah,
along with this,
yeah.
because differences and differences
Right.
and differences.
Yeah, that may be something.
Okay. I was trying to figure that out because I know you don't want a tall tree, you want more of a wide tree, right?
Yeah, but if you end up with a tall tree, you end up with a tall tree.
Oh yeah,
It's
you
still-
end,
it's
yeah,
still valid.
you end up with it, yeah. I was saying like, yeah. I'll try another example.
Okay.
And see what I can do. Or we almost done.
We're almost done, so, okay, so I think people are good with this, so if you see this on a test, you're okay with this, right?
I guess.
Okay. Somewhat? I'll take somewhat.
There's no wrong answers because we can build trees all different ways, right?
There's almost no wrong answers. So how do we code something like this? And the way that we've been doing it is sort of a nod to the fact that we have whiteboards and we can't move things around easily. But it's not really as mysterious as that. If you start with your original frequency table, we can basically just write all these nodes down. A is a 5, B is a 3, C is a 2, D is a 1, E is a 6, F is a 3, and G is a 2. And we can think of each of these as the root of a little tiny tree that has only one node in it, right? And our algorithm is now just find the 2 roots with the smallest value and make them children of a new root. And that's all we do at every step, find the 2 roots with the smallest value, make them the children of a new root, right? So it's hard to do on paper like this because we'd say, okay, well, 1 and 2 go together. So that becomes a 3, and now what are the 2 smallest roots? Probably, let's do the 3 and the 2. So that becomes a 5, and now what are the smallest roots? Probably the 3 and the 3. So those go together and become a 6. And the drawing will become ugly, right? But in practice, this is what we would do in code. Start off with 8 little trees with 8 roots, and as long as we can go through somehow and find the 2 smallest roots, right, the 2 trees whose value at the root is smallest, we make a new node, we make those the 2 children, we remove those 2 nodes from our list, and we put that new root in, and now we look for the 2 smallest. And it's a pretty short algorithm. But here's a question: how do we figure out what the 2 smallest values are in our collection at each point? What kind of data structure could we use? Yeah, min heap would be perfect for this, because that's what min heaps do. They let us pull off the smallest thing by just grabbing what's at the root, do your reheaping, grab the root again, there's your 2 smallest things, put them together, add their values, put that new value back into the heap, reheapify. So now you've got 2 smallest things ready to go, and pull those off and just keep doing this until you've got 1 root and nothing left in the heap, and then you're done. And then you just do a series of traversals to print out the code. So it's really not that bad to code up. You got to sort of pin down the data structures, your nodes have to have, you know, a letter and a total frequency associated with it, but that's not too bad. So this is fairly painless to code, maybe in 223. It's a real common programming assignment. You'll definitely do it at some point. All right, so those are Huffman trees. We didn't get to talk about decision trees. We'll talk about decision trees next week. Decision trees are another type of binary tree. We're actually going to use them in 223 for one of your assignments. But it's a basic way to play the 20 questions game. So 20 questions, somebody thinks of something, and then you get to ask them 20 yes/no questions. And based on their answers, you try to figure out what they're thinking of. And we can code the knowledge that you need to play that game well as a type of binary tree. So I talked about it a little bit at the end of the previous lecture if you want to watch that, but we'll talk about it sometime next week. All right, so Monday, presentations by each group. I'll have a laptop here connected to the server. And then we'll wrap up the course next week. So, cool. I will see you next time then.